We're starting our look at circle proofs with basically introduction or recap of some basic terms. Now, when we're talking about a circle, there's a few ways of considering what a circle is. We can consider a circle as a conic section, for example, and a conic section could be the well-known ones are circles, ellipses, parabolas, and hyperbolas. And basically, they're all derived from a cone, hence the word conic, and it's when a plane is passed through and the shape generated at the interface when the plane is horizontal is a circle. If we tilted it, we'd have an ellipse, provided we don't tilt it as much as it being the plane being parallel with one of the sides, the slant sides of the cone. If we take it further too, we get a hyperbola, but the important one there is a circle. That's purely just for some background. Another way of looking at a circle is a set of points. So we could say it's a set of points P in a plane, and those points are equidistant. From a fixed point. From a fixed point known as the center, which we might want to call C. So we know that as a circle, so it's a collection of infinite many points that are all equidistant from the center C, and that distance is the radius. Okay, so we're talking radius there. So whether we could say that explicitly or not, we knew that that's basically what a circle is. So we could represent that here with the center C, and an example of the collection of points P. There's one there, and P would be, if we're looking at it in a Cartesian sense, it'd be some point XY, and we'd have to name the center something else. So HK, the coordinates of the center. And if we take a look at that, we've basically got a right angle triangle that can be generated, and this here, this distance is y minus k. This distance here, i.e. that distance there, is x minus h. And so an equation for a circle, not that that's hugely important for right now, but for background information, equation of a circle is x minus h all squared, y minus k all squared, equals r squared, using Pythagoras. If it's a circle with the center at 0, 0 at the origin, it would simply reduce down to x squared plus y squared equals r squared. Okay, so defining a few terms here with the aid of some diagrams. Got a circle, we've got a point A and B. If we pass a straight line through there, okay, I'll have to give the slight waves in my line. The whole line itself is called a secant. So the purple line is called a secant. If we only look at the bit passing between A and B within the circle, here, that's called a chord. So a chord is part of a secant. Both are straight lines. Now, between A and B, there's another way to go. We could go along here, take part of the circumference, and that's called an arc. You're probably familiar with that one. So it's a curved path along the circumference. We can now define segments. So on the circle shown, we can see a major segment and a minor segment. So the major segment I'm going to shade in green. So that would be this segment here. And the minor segment I'll shade in blue. You can see in both cases each are a region which is bounded by a chord and its arc, or you could say bounded by an arc and its chord. So the major one is bigger than the minor one. So a segment is an area or a region. Another important word is subtend. So we'll add that to our glossary. Subtend. So you're bound to hear that a bit. On this green circle here, I'm putting in a point A, a point B, and a point P for point P, and we've got some straight lines, chords in fact, joining A and P and also B and P together. Now if we put in this angle here, I'll put it in black there. If we call that angle X, angle X, or in other words, angle A, P, B, makes use of the word subtend. In fact, it's the angle subtended by line or chord or path AB, even though AB is not marked in there, at P. So in the journey from A to B, you could say there's an angle subtended there at P. Lastly, before we're ready to do some actual proofs, we need to remind ourselves of our congruence theorems, or rules if you like, or laws from junior. And congruence means identical, and so we have SSS, where we have the three corresponding sides matching in length. And remember, this is not similarity, this is congruence. This is identical triangles which might be translated only or rotated, but the sides are the same length and the shapes are the same in congruent triangles. So we have SSS, SAS, and remember A is the included angle. Notice how it's between the two given sides. The sides correspond, you can see by the notches there. And then we have AAS, so we have two angles and a side of one triangle are congruent with the other two angles and the matching side. So these things must correspond, okay? And there's a special case, RHS, so if we have a right angled triangle, hypotenuse and a side of one triangle are congruent with the hypotenuse and the matching side on the other. Alright, we're ready to start some proofs involving circles.